How's it going, everybody? Hope you're all doing all right. CGO Clan, what's up? How's it going? I got distracted because I saw this horrible symbol pop up in the bottom right of my computer screen, which you can't see, but it's a Windows update. Anyways, today we are going to be talking about tessellated paths. I am running this in debug mode, and you'll realize, hopefully, you can see the difference. This is much, much faster than it was before. And the reason it's so much faster is because I had first year. Yes. Is your sentence fixed? I'm not sure. We'll have to check that out. But basically, I had an epiphany Sunday morning and realized that I'm very stupid and I was making all of this way more complicated than it had to be. And I realized I can just cache the SVG like this, right? And so we just have one cache of the full SVG and we can just fade that in. And then I can draw these paths using triangles. If we switch to wire mesh view, you can see these are just triangles going around. And yeah, this has much higher quality and it is way, way faster. So I don't know why I didn't think of this before, but very happy with the performance so far. We're going to keep going down this vein and fixing up some other things that are also broken. And the first step for doing that is going to be refactoring some of the code because I didn't implement this in the best way possible. So we're going to be taking a look at how the tessellation happens, refactoring that a bit. This was just kind of proof of concept to get it working. And then once that's refactored, we'll move on towards some other things. But yeah, very happy with this. And this is all splitting up very nicely. This is a bad spot right there, but I'll have to take a look at that and figure out how we can kind of smooth out these kinds of issues in the future. For now, though, it works good. Another thing that we're going to have to fix, too, is if we go to the W, you'll notice that these miters go very far down. So they kind of extend quite a bit there. And the reason for that is because I haven't implemented something which normal SVGs do. This is Inkscape, so I want to see what they do. Notice how if I bring this corner down, if the miter is smaller than a certain length, and the miter in this case is just the join here, if that's smaller than a certain case, it switches to a bevel, which is where you see it flattens out at the end there. So if it extends past a certain point, it switches out to that bevel. And that is something that I will have to add as well, just to make sure that we get that, because right now we have this artifact, which is these W's, which they extend way too far. We should be cutting it off kind of like right there. And you can actually look up exactly how this works. The SVG spec gives you some information on that. The Mozilla docs are actually really great on this. Actually, I don't know if it's this one. Yeah, this one. So basically you can see when the miter join has been specified, the ratio is defined as this, and if it exceeds this ratio, then it cuts it off at a certain distance. And they kind of give examples here, and they give equations that you can use, and you can figure out. And you can see that they give you kind of like what it is, and you can look up the default values of this and everything. So great stuff. I'll be referencing this when I go to implement that part. But the way it'll work is the same way that the rest of this works, which is basically we will just tessellate it, and we'll just create a triangle that ends right here. And so if you can kind of see, there's actually 4 triangles here that all join at that end. And so we can switch it up easily to kind of make a more well-defined quad and do the same thing. So how am I doing this tessellation? How does this even work? Because that was actually not as simple as you would think it would be. These joins are a lot more annoying than you would think. So joining up these edges, what happens if you don't have miters is you end up getting this kind of effect where you get these splits. And you can see this. This guy has kind of like a whole article on this where basically, right, if you're not joining these edges correctly, and I hope you guys can see this. Maybe I can zoom in a little bit too. Yeah. You can kind of see how it splits there, hopefully. And so the problem with this is the reason it's splitting like that is because the quads, if you don't actually have them joining together, then you're going to get that white space. And even if you increase the number of segments like this, you'll see you'll still get those segments split on certain parts. And so this article kind of takes you through, well, this article takes you through how to solve that for Bezier curves, right? And so this is what I used for the Bezier curves portion. So when we have curves like this, that's what I'm using to join those. But when you're talking about line segments and joining actual line segments and stuff, that's a different case. With Bezier curves, what you can do, and you can follow this article too if you're interested, is basically you can take the derivative of your Bezier curve, and then you can go ahead and figure out exactly what the normal is at that point. Yes, right here. So you can find out what the tangent vector is, and then you can find out the perpendicular vector, and you can use that perpendicular vector to define how to join them. How's it going, Asher? Good to see you. So that's essentially what I did. And you can actually see this too. If we go into our renderer and I go down to draw line, or actually I think it's Bezier 2. Yeah, there we go. So basically what I do is I go ahead, I interpolate, so I get the point that I want to draw for this quad. Then I get the normal, which is actually the tangent in this case. Normal has too many definitions. It's overloaded. I should be more explicit in my code, but it is what it is. And I basically pass that to this line to 3D function, which takes that normal and uses that to define how it works. And I actually might not be using that now that I think about it. No, yeah, okay. So yeah, that normal basically gets stored away in code. And then what we do is once we close the path, we go and we figure out how to join all these line segments together, right? So we go loop over each of the points in the path, and we want to generate these quads so that they actually join up properly. We get the correct angles for all of these, and it all looks right. And it has a uniform stroke width, because that's really what this is all about, is making sure you have that uniform stroke width so that it's consistent, right? That's the whole reason that you're doing this. And so the way you can join those is, let me switch over to the drawing stream real quickly. The way you can figure that out is, say you have a line segment like this, right? Where you have a path. So you have this point goes here, goes to here, goes to here. How do you figure out what angle this needs to be and what angle this needs to be and how tall each of these portions need to be? Well, what you can do is you can first find the bisecting vector between these two. And the bisecting vector is actually pretty easy to find. So say we want to find out which vector bisects this, we would get the unit normal in this direction, the unit normal going out in this direction. And then if you just add those together, so if you were just to stack these vectors on top of each other, kind of like that, what you get is a vector that looks like this. And that, so right, we get something that looks like that. That's actually perpendicular to this guy right here. And so what we can do is we can just take the perpendicular vector to that by just swapping the x and y components, and you get the bisecting vector. So that's how we get the vector, the direction, but we also need to figure out how long it needs to be. And we can do the same thing over here, so we eventually get this length. How long does it need to be though? And this was the point that really tripped me up for way longer than I would like to admit. You can get how long it needs to be by saying, okay, I need this direction is the direction I need, right? And I need it to be this big, right? This is the stroke width. This distance right here is our stroke width. So this is how long you want it to be. Well, what can you do? You can just project this point onto this direction. And it really is that simple. So if we just go and we say, okay, let's project, or I guess technically you're projecting this onto this. If you just project it, then it gives you exactly the point, the distance you need to be to maintain this width. And then you can do the same thing over here, and you just project and you project, which in math is just a dot product. If you're using unit normals and stuff, it kind of works out that way. So you just use some projection and some vector addition, and it's a lot simpler than I made it out to be when I was first implementing this. Took me way longer than it needed to figure this stuff out. Some other resources, if you're interested too, was this thing, which is particularly helpful. It kind of talks about how to find that bisecting vector, and it talks about the normal and everything. I don't really like their explanation of how to solve the rest of the stuff, and they kind of do this triangle in between, which I'm not sure why. So I don't do that. I don't think I need to do that either. But yeah, I kind of just use that as like a little bit of a reference to see what they were doing and modify accordingly. But if we take a look back at the code too, you can see I'm doing exactly what I said I was doing there, which is we basically get the, well, you can kind of ignore this stuff. That's just extra stuff that we're going to clean up when we refactor. What we do is we generate a miter. And when we look at that, we get the direction from the going in vector, and we get the direction from the going out vector. So direction A and direction B. Then we get the bisection, which is we just add them and normalize it. And technically this is the tangent to, or the perpendicular vector to the bisection. So I kind of had these confused, but it works out. It's still the same thing. And then what we do here is we find out what the perpendicular direction is to that normal that we want to project onto. So then we get the bisection. We store that in our out normal. And then to figure out how wide this particular join needs to be, we project the stroke width onto the bisection projected onto the second line, right? And that's what this is kind of doing. So we project that onto that, and then we divide the stroke width by that to get kind of the normal length that it needs to be. So projection and then scale. And then it all works out. We get the correct miter kind of reference, and we get that for like the start point and the end point. So in this case, if we took a look back up here, when we're doing one line segment, we need two miters, right? We need what is the length of this guy and what is the length of this guy. So we get this one and then we get this one. And that's what this code is doing. We get the first one, then we get the second one. And then we go ahead and we get, what is this doing? Oh, and this is just some like edge cases. Basically, if you're, whoops, let's go back here. If you're at the beginning or the end of a path, you don't actually want to draw a miter, right? So like you'll notice right here, we just use a flat end, and you can actually change that to like be an arrow tip or whatever you want it to be. But the whole point is this does not need to be mitered because it's not connecting to anything. And so that's what this code here does, is it just checks those edge cases. And same on this one. That's exactly the same thing. So we're checking the front and then the tail of the line or the path. And then we just draw the line. And so drawing the line, if we jump into here, basically uses the directions that we passed in, and then it just calculates two quads, and we draw two triangles to fill out that segment of the line. Yeah, and there's extra stuff in here that I haven't implemented quite yet. So that's how it kind of works. I hope that made some sense. And if you're ever looking to do this stuff, it is very annoying. So yes, just be warned. All right, but now that we have this done, I wanted to clean up the code. I finished this pretty late last night, and I was like, okay, I will finish this up in the morning. And I figured it's a good way to talk about it and stuff too. You'll notice if we go back here that this is actually in something called endpath 3D. I don't like that. This should not be in its 2D stuff, but I called it 3D stuff for who knows what reason, because that's what I was thinking at the time. Or I was just modifying some stuff at the time, actually. But anyways, we're going to fix that. So basically, we want to go ahead and just refactor this code so that it reflects what it's actually doing, which is all 2D. It's not 3D line stuff, it's 2D line stuff. So we're going to do this. And we're going to have something similar to this API where we basically have all these functions available to us except for the 2D case. And so we'll have begin path. And this is kind of like how I do it, is if there's a 3D at the end, it's implied that it's 3D. Otherwise, it's implied that it's 2D. So that's kind of just the API standards I've chosen. So we'll have conspec start normal. And we might change some of this API too. So right now, I'm just going to copy all this stuff, but I may change the way some of this works. So then we're going to have end path. And close path just tells you like whether you're actually going to draw a connecting line at the end when you close the path. We're going to have line 2, Bezier 2, 2, and then Bezier 3, 2. And I might actually change the semantics of this too, because in SVGs we have path commands, and I think I'd like it better if we reflected what these are, which I think it's quad and cubic. Yeah, so we have cubic curve, which is 2 points, and then we have the quadratic curve, which is 4 points. But they call it S. Why do they call it S? Okay, yeah. Yeah, quadratic is Q. Or wait, no, quadratic. See, this is always confuses me because quadratic sounds bigger than cubic. But in this case, quadratic has 3 points. You can see we have connecting and then endpoint. Cubic has, if we look at this, 2 connecting points and then the endpoint. So, and the reason they're called quadratic and cubic is because of the shapes they form, right? If we looked at Desmos, I'm sure you guys know this. Okay, yeah, if we do x squared, which is a quadratic curve, it's a parabola. But if you do x cubed, you can get a snake shape kind of thing, which is a cubic curve. I have no idea why we decided to call 2 a quadratic. It makes no sense to me, but maybe somebody out there who knows math better than me can describe why we decided 2 would be a good idea to equate with 4. But anyways, all that to say, let's name this quadratic. We'll do quad 2 and then cubic 2, just to kind of like keep it in line with the SVG path spec and have that the same. Quad has 2 chords. Yeah, I know, that's what. How's it going, by the way? Yeah, hi Sam, good to see you. But yeah, that's exactly why it confuses me. Quad has 2, but if quad means 4, right? So if you look up just right, because quadrilateral and everything, that means 4. Yeah, so you have quadrangle, quadrant, all this stuff, which basically quadruplet 4, you know, quadriceps 4, quad bike 4. So I don't get why they decided to use that. Like usually use bi to describe 2, quad is 4, and then cube is 3, right? Cubic or tri is 3, I guess, but don't know why they decided. There's probably some higher level math thing that describes why that's necessary. Okay, so let's go. I'm not sure if we're going to actually have these. Yeah, I think we're just going to keep it like this. Okay. And then let's go ahead. We're going to implement these, which are basically just going to be me copying and pasting from the 3D paths and then modifying some stuff slightly. So we'll go ahead and do that. And then I'm going to modify the 3D paths back to what they were. So let's go. Where was this? That's not what I want to do. Okay. This was above begin path. 3D. Okay, cool. So we'll do that. And then let's go ahead and copy this little preamble thing so that we have that in the code. And we will go ahead and just add these guys in there. That. Okay. Yeah, and I think that's good. Cool. And then we want to change all these to vec2s as well. So let me just do that real quick. That should be a vec2. Vec2. Same here and here. All right. Cool. So that's good. And then let's just change these up. All right. So now we got vec2s. That's all good. Cool. So the way that I do these paths are, they are kind of stateful. I might actually do the 2D ones a little bit differently too, just because it makes more sense, I think. So the way I was doing the 3D paths is if we go somewhere up here. Okay, yeah, somewhere up here, we basically have a bunch of state. That's just kind of global state, and I don't like that. I've been trying to get away from having global state because it's not good. Yeah, this is what we have. So we have this path 3D vertex line, which just has like a max path size. And I think it'd be better if we actually did. First of all, we need a struct for our 2D lines. So we'll have a struct. This is going to be path vertex 2D line. And this is going to contain a position, a normal, a thickness, and a color. And I'm actually going to do a vec4 for the color because we don't need to pack it at that level. Cool. So what we're going to do is we're going to have this. And then I'm trying to think of what the best way to do this is. I think what we're going to do is we're going to also have like a struct path vertex 2D data or something. Or actually we can do path 2D context, right? And this is just going to have a vector of these. No, we can't quite do that. So the reason I kept it as a, well, I guess we can. It really doesn't matter. So this will be tightly packed in C++, right? We don't have to worry about the memory being non-contiguous with a vector. So I guess this is fine. And this will be our data. And then what I'm going to do is I'm going to forward declare this out in the header file so that anybody using this will have access to that API. And then what I'm going to do here is this is going to return path2D context star. Okay. So basically what this is going to do is it's going to keep the context around. And then when you're creating your path, you're going to pass that context to each individual part. We'll just call that path. And the reason for this is because then I guess we could like add these onto here and stuff too, but we keep the data opaque and it is also pretty simple. There's nothing complex about this. And this means that if you have like multiple threads operating on this stuff, that it's up to the user to define how this stuff maintains thread safety and everything. And I don't have to worry about that as the library maintainer. So all better for me. And kind of in that vein, when we have this set transform as well, we're going to have to add that to our context. And so we can add extra data here, which is like the transform, color, whatever. I'm trying to decide whether I like this or not. I think I do. I think this should be fine. Yeah. Okay, that's how we're going to do it. So yeah, we're going to do that. And then once you end a path, I guess that's going to free this memory. Is that a good API design too, though? I don't know. Maybe we should have a separate free. Yeah, that probably feels a bit more explicit. Okay, so we'll basically have an API like this where we can begin a path and then we can do that. Let's go see how we're going to use this. So inside of svg.cpp, we have a lot of stuff. Don't know why I have all this commented out too. Actually, I think I do. No, I don't know I have all this commented out. We'll have to revisit that too, see why I commented that out. Okay, but anyways, there's a function here called render outline. And this is what actually goes ahead and like calls these path functions and kind of tessellates it and all that stuff. And so inside of here, what we're going to do is we're going to change this up to this. And what we want is for each path, which is the loop in here, we will basically go ahead and say, okay, let's create a path 2D context star. And that's going to be null pointer. Let's just make sure we're including render.h. We are, okay. So we're good there. So we have our path 2D context, which is null. I'm trying to stay out of this sunlight. I really need to get some curtains. Okay, and then once we get into here, we are going to say begin path. That's 2, and then we can get rid of that. And we can say context equals that. Or maybe just call it path. Nah, we're going to call it context. That makes more sense in this case. Okay, so we have the context. That creates the context. And then once we get into here, we can say assert context does not equal null pointer. If it does, we have bigger problems. My assert messages are very bad most of the time. So if I ever run into these asserts, I'm like, okay, what does this even mean? Make your assert best messages better than mine. Anyway, so once we do that, we want to get into here, and I'm going to replace the API calls that we have in here. So we have this context. As we go through the curve, we want to actually go to each of these places. So what we'll do here is we'll say quad 2, and we want to give it our path. And then we want to give it P1, P2, and P3. Okay. And it's not, oh, we actually want to give our context because that makes more sense. Oh, and this is actually cubic 2. There we go. So yeah, we want to do that. For this one, we want to do the same thing, except this is PR because it stands for projected, but I never actually project anything because it changed and all that stuff, but it is what it is. And then we're going to have line 2. And let's just go ahead and do that. And this is going to go to P1 and take in a context. And then finally, once we are done with everything, we're going to go ahead and say end path. And we're going to give it our context. Yes. And then we're going to say render free context. See, I don't know if I like this. We're going to roll with it, though. We'll see what happens. Okay. Same thing here. And there. Cool. So we're doing that. One last thing, too, is I do want to set the transformation for each of these, which right now I'm doing up here. So instead of doing that, we're going to say up here after we create our path. Ooh, does this work right? That's a good question. Okay, so first of all, let's go ahead. We're going to say this returns a path context 2D star, or a path 2D context star, like I said. And then we just want to make sure each of these takes in one of those guys. And we'll call it path in here because it doesn't matter too much. Okay, so we'll grab that, put it there, there, and there. Okay. Cool, so we got that. And now what we want to do is we want to go to our 3D stuff, and we're basically going to do the same thing here. So now I can get rid of some of these things. So because it was global state, I had to kind of keep track of whether we were drawing a 3D path or not, because otherwise you could break stuff. Now we don't have to worry about that because you don't have to worry about it, which is good. We do have some other global state, but I think I'm going to keep that global for now. Maybe I shouldn't, but I don't know. It doesn't seem like a big deal to me. So we've got that. Yeah, okay, so we have the translated position. This is where it's going to get. Yes, so we actually need to modify this slightly. When we begin a path, you need to optionally pass in a map4, which is your transformation, and this will be initialized to our identity. Right? Okay. So let's just do that, and then this will take in map4 reference transform. All right, so then we get that, and let's also go up here. We're gonna say path 2D context star context equals that, and then we just want to cast, whoops, lost that. And then we want to do a placement new, just to actually initialize the C++ stuff in there, because we've got vector and a mat4, so that'll call the constructors and stuff. Okay, so we do that. Then what we can do down here is we can say context transform equals transform, and then instead of doing this, we're gonna say context transform. Right, And then what we're going to do here is we are going to say path 2D vertex. Path vertex 2D line. It's a mouthful. This is our new vert, and we are going to say vert.position, all that stuff, except we don't have to worry about that. So we'll do that. The color is not going to be packed, so this makes it a little bit easier. We have a GLM vec4 though, but I think I have CMath to vec4. No, I think we have a... I'm trying to think of how I labeled this. I think I have something that converts between them. Let's go into where this is defined, vec2. 3, 4. No, okay. I could have sworn I had it, but maybe not. That's too bad. Okay, whatever. So we'll just do this then. Initialize it in line here. And say this is color.r g b a. Okay. Then we get thickness, the normal, and I think that's it. And then we don't need to do that anymore either. Cool. But we do need to push this. So then once we do this, we'll say push data.push vert. And that's the first vertice in our path, vertex in our path. So this is how we start the path. Adding additional lines to the path is pretty easy. We modified our API though, so we do want to make sure we fix it in here. So here we're going to say parent global transform instead, and that's going to set the transform as well as all the other stuff. Okay. And then I'm going to go ahead and remove this. Well, I guess it's still useful. You might want to do that in the middle of it. Yeah, I'll leave that. Okay. Anyways, we'll save end path for later. Line 2, let's get that. So we'll copy all of this one. And then we'll just modify it slightly. Okay, so we don't have to worry about this, which is nice. I guess one thing we should probably do is assert that the path is not null. So kind of like just a sanity check. But yeah, we're gonna do that. Well, okay, so we can do this, or we can change the API slightly and change this to a reference. Nah, I'm just gonna do it this way. Because I was gonna say then the runtime can catch it itself, like the C runtime, or C++ runtime, I guess, I don't know. But in debug mode, it catches that stuff and just tells you anyways. If you try to dereference a null pointer and turn it into a reference. Okay, anyways though, we'll just add this. Put that up there. And this also needs to return the context. So that's also important. Cool. So we do that, and then we don't need to check this. We get that stuff. Let's change this. We don't need the packed color at all. Okay. We need to translate it, so we do that. And this needs to be context transform. Or I guess path. Yep, cool. Okay, yeah. So we do that. Position, color, all this stuff. And this is actually going to be, what do we call it? Path, vertex 2D line. Okay, we'll do that. Vert. It's going to be vec2. Okay, and then this we're going to change to be the same as this one. And then we're going to go ahead and just say context or path data.push And I guess we could do in place here because we aren't using this afterwards. So we'll just use in place back there. Same thing here. Cool. So that should add it to the path. I'm just making sure I didn't miss anything there. That all looks good. That's fine. That's fine. Cool. Okay, so then quad 2, which is Bezier 2. And we're going to copy this. And paste it here. Let's go ahead and just copy our assertion. Okay, so for this one, mostly the same stuff. There's slight differences though. We don't want to use this. Okay, so we basically get this is the control point, this is the end point, and then we can get the first point from our previous point there. And that's how we're going to kind of interpolate. I'm just making sure we don't have that here. We do not. Okay, cool. So we can get our previous point by just looking back in our path from here. Yes, and we should always have one because when you begin a path, you have at least one position. We can also, though, just say glog or assert path data.size is greater than 0, cannot. Okay. Just to make sure that this should always be true. So we do this, we transform them. And then what am I doing here is what I'm wondering. First though, we're gonna say this is path data. And this is gonna be a vec2. Okay, this is also going to be a vec2. So then we're going to estimate the length of the curve so far so that we can split it up into different segments, and then we're going to join it using line segments, kind of like how this article right here described. So basically, we estimate the length and then we auto segment the path. So we just add these lengths up and then use that to determine how many segments are going to be in there. So that's exactly what we're doing here. I basically just go ahead and I don't think these are translated at all. I think these are just, yeah, I'm not sure what I'm doing here. P1. Oh, these, okay, yeah, these are the translated ones. So these are the transformed ones is probably a better word for that. Transformed. Yeah, okay. So we'll do that. Wait, but then we do have transformed? Oh, and we have P0 and P1 and P2. Oh, okay, okay. This is also transformed. Okay, that's what I was looking for. So we'll have that, and that. And these are going to be vec2s. Okay, then we get the length of those. Transformed P2. And what was that? That was P0. Okay. So do that. Okay, we get the approximate length, and then we can use that to determine how many segments there are. Then we're going to split this curve up into that many segments. So we basically use T to interpolate. We get this transformed. Change all of that. Okay, we get the normal and we get interpolated point, and then we can say line 2, the interpolated point, using, oh, and we also need to pass our path. And then we don't want to apply the transformation because we've already applied the transformation, and then we're giving it the normal that we want it to use. Okay, and so what that's going to do, and then at the end, we also do a line to translated P2. I'm wondering if this is necessary too. We technically shouldn't need that. Unless I do this. That's better. Okay. Transformed P2. And we also need to give it the path. All right, so basically what we do there, right, is we go line 2, line 2, line 2, and we give it the normal using the derivative of this Bezier curve at that point. And then we use that to generate kind of a bunch of lines that go into it, and it creates the curve shape. So right now I just have it applying a fixed 40 times, which seems to work all right, but we might change that because I don't really like the granularity it has right now. So we'll revisit that. Anyways, though, Bezier 3-2 is basically the same thing. So that's our cubic 2. Oh, and I lost my copy paste there. There we go. Okay, let's grab this. Copy that. Cubic 2. Okay, and we'll do that. And we also want to make sure that we actually have some elements in our path. And then we'll just log an actual helpful assert message if we need to. Cool. So then this is 0. All right, we get that. Let's call this transformed. Right, okay. Let's just do a replace on translated to transformed. And we'll start from here. Replace. Okay, cool. So that's what I wanted, and okay, we're still here. So we've got all that. This is not transform 3D. We want to use our path transform. And I did do that up here as well. Cool. And we also want to make sure these are vec2s because this is coming from path data. And this is also coming from that, which I don't think I changed up here. Yeah, that would be a bug. So let's make sure we fix that. Cool, so that's good. And then these are all going to be vec2s. All right, that's all good. These are all vec2s. All right, and then that stuff's all good. Then we're just going to modify this as well. Go to -1. And this should be from 1. Yeah, okay, so that's important. I don't know why I had those wrong. Okay, so we're going to fix this. This is going to be a vec2, vec2, and then this is going to be a path, and a path. Okay, cool. And so that should do the same thing, just for a cubic Bezier curve instead of quadratic Bezier curve. And then we have this set transform, which is just going to do path transform equals transform. So that's easy. Okay, and then end path is where all the hard stuff actually happens. So end path. Yeah, so if we go into here, this is where like the majority of the actual logic for the path generation happens. Let's go end path. Yeah, cool. So we got this. All right. So trying to see which way is best to get out of the sun. Okay. So in here, what we do is this thing, which is, so basically if we're closing the path and the starting point equals the ending point, I subtract it by 1 because otherwise you get errors. That's basically why. I'll leave it at that. We might visit this later and see what happens when we take this away, but I'm pretty sure you get errors when that gets turned off. But anyways, what we want to do too is we want to say int end point, I guess, equals path data.size. We'll go ahead and cast that to an int. And then basically we want to say endpoint minus minus, and we'll be looping through that. Okay, and then we want to say path data vert.position, and we can change this to a vec2. We'll kind of go through what's happening here in just a second as well. Okay, so this is endpoint. That's that. That's that. This is endpoint. Let's kind of do a find and replace so that I don't miss anything. So we want to replace these with endpoint, starting from here. So we'll replace, 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 replace. And then here we can just kind of take that out. Okay, cool. So that's good. We've replaced those. And then we want to replace this with path data. So replace, 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 all that stuff. That stuff as well. And that's good. Okay, cool. And then we just want these to be vec2s. And I can get rid of these transformations that I had to do, because the only reason I had to do that was to convert from 3D vectors to 2D vectors. So we can get rid of all that. I need a generate miter 2D or something, or generate miter 3D and 2D. This is going to be a vec4. And we can get rid of this. Okay. We're gonna, yep, that's all fine. That's all good. We're gonna fix this in just a second. And what's wrong with this? This is next pose minus current pose. Oh, we just want to change that. So we can get rid of that. We can get rid of this, which is nice. And then we can get rid of a lot of this stuff as well. Cool. Those conversions were only necessary because I was trying to stuff all this stuff into a 3D API for some reason when it's all 2D stuff. Okay, it's good. So then let's go find generate miter, and we're going to go ahead and copy this function. And we're actually going to make 2 copies. So let's look for all of our static functions, which are kind of like the private functions. So if we go up here, there should be, okay, yeah, these things. This is what I was looking for. So we're gonna have generate miter 3D, and then generate miter. This is taking vec2s. And then we'll go down to get stroke width. And we'll go ahead and implement these. Hopefully this is interesting for you guys. I don't know if refactoring stuff is really that interesting to watch. I enjoy it when I'm watching like Jonathan Blow and stuff, because I kind of get snippets of what he's been working on, but I have no idea this is any interesting to you guys. So if it's not, let me know and we can do other stuff at some point. Let's fix this. So that one's fine, and then this we can just fix because we can do that. Make this simpler. Okay, and then let's go find where we were calling that for the 3D APIs. Yeah, because we want to change these now to be 3D and 3D. Cool. Okay, so now this is good though. So what's happening here when we end the path? So basically, we've just gone ahead. We've, technically finished, if you're calling the API, which we do from the SVG. We finished going through this, and doing all of our quad 2, line 2, cubic 2, all that stuff. And we've called end path. And so what I'm doing at this point is I'm going to loop through each of these points, and I'm going to tessellate this into an actual curve. And so we want to basically create triangles that form these shapes as quads, right? Because technically this isn't a line, it has thickness now, so it's actually shapes that we're trying to generate. And so in order to do that, what I do is if we go back into our renderer, we first of all just check and see if the path is closing on itself, right? So if the path is closing on itself, we want to do something a little bit different than like if you have it closed automatically. I don't even know if I can do this in Inkscape, but I assume I can, where I can say like close the path automatically. But cannot find it, but I assume you can, where basically it automatically creates a line from there to there when you're done. So that's all that's checking for. Then what we do is we have to get our positions. So we get our current position, our next position, our next position, and our previous position. So say we're looking at this point right here. We get this is the current position. We get this is next, and then this is previous. We need all these. Why do we need these? Because we need to determine what the direction is going from here to here, from here to here. And then to generate this part of the quad, we need the direction from here to here and the direction from here to here. So in order to get those, we need all those points. So I basically go and I get each of these. But you have to worry about the edge cases, which is, oh, what if I'm here? There is no next position. There is no next position, unless, of course, we're closing the path, in which case this would automatically be joined to here, and then I would just loop around to the beginning and then keep going. So if that's the case, I basically just do a modulus if you have the path closed. If not, then I just set it to be this position so that we know that this is the end point. And so that's why there's a bunch of ternaries here. We're basically checking, hey, do we have enough room? If we do, we actually get the position. Otherwise, if we're closing the path, we do a modulus. Otherwise, we just take the last position that there is. So we just get all that data. That's all that's happening up there. We get the color, we get the thickness, we push those onto our stack so that we can actually generate the lines and stuff. And then we get the first normal and the second normal. And the reason we get this is because the way I've designed the API, you can supply a normal if you want. So like, say you generate, let's do this. Is this gonna work? No. Am I using the wrong thing? Probably. No, I think this is right. I think Inkscape just doesn't work right. Okay, there we go. Yeah, so say we draw this, and let's increase the width. And let's say this is actually like attached to this line. So basically, if you have something like this, what I do is for all these in-between points, as I'm tessellating these, I manually supply the normals for each of these connecting segments, because I can use the derivative of the Bezier curve, which is going to be more accurate than doing miter joins around that. So basically, I have the option here where either you can generate a miter or you can supply the normal yourself and kind of do all that yourself, which is the whole point. If we're generating a miter, we need to know how thick that miter join is. So we need to know how far out do we go from the center here. So if we click back into this, is it going to give it to me? Inkscape is struggling here. I don't know why, but it is struggling. Let's see. Can we do edit? Maybe? No. Path. Okay, anyways, imagine there's a point there because Inkscape apparently isn't working. We need to figure out how far we need to go up this way and how far we need to go down. And then for this point, it's a different length, right? So you'll notice that this is actually technically, I can't zoom in or out. Okay, Inkscape is broken. I don't know what's happened, but technically this is longer than this join. And so that's all I'm doing here is I'm figuring out how long the first join needs to be, how long the second join needs to be. We generate the miter, kind of how I talked about earlier, for each of those based on the positions. You can see we use the previous, current, next for this, and then we use the current, next, and next for this to get the appropriate directions so that we can project and do all that stuff eventually. Okay, once we do that, we need to check and see if we're at an endpoint. Because if we're at an endpoint, there is no miter. We just want to cap it off like this, or you could cap it off with different caps, right? You can see right here in Inkscape, you could have a rounded cap, or you could have like that, or some sort of whatever. We're not doing any of that, but in case in the future we want to do that, we have the option. For now, we just apply the normal using whatever the direction of the line is. And then otherwise, we take the next position. We do the same thing for the endpoint. This is just checking the endpoint, which has the same kind of constraints. And then finally, we draw the line using all that information. And if we jump into here, This basically just gets the bottom left, bottom right using the perpendicular vectors we passed in and the thicknesses we passed in, and draws two triangles. That's it. Harry Studios, what project is this for? This is for, is this going to work? First of all, hopefully this works. This is for this project I'm working on, which is to create mathematical animations for my videos. In the past, I used 3 Blue 1 Brown's Manum, which stands for math animation, except I had some problems with it, and so I'm essentially creating my own, and we'll see it in just a second. First, I gotta fix this. Render free struct path 2D context star. Unresolved external symbol. We don't have that defined. We need to define this. And I'm actually gonna move this up to begin path, because that makes more sense. Okay, so begin, there we go. And then for this, we're just gonna say tilde path 2D context, and we're gonna call that on our path. Okay, so we're gonna manually call the destructor since I've allocated this memory. A little bit weird, and then we're just gonna free the path. Cool. So we got that. Now we can see what's happening here. We should get exactly what I talked about, and we've refactored it so it's nicer. It's a little bit better. Okay, so we've refactored it, but it's clearly not working right. Looks like our Bezier curves are broken. Let's fix that very quickly. Cubic 2. So we've got that. Okay, that looks fine. I wonder if it's the quadratic too. So that's false. Wait, let's see. False, false. That's fine. Just making sure. When we do line 2, okay, I say if apply transform. So that's checking that. So we get this. That multiplies there. Let's get to the last point. Oh, am I never... Wait, no. Yeah, this is fine. Okay. Okay. This all looks fine. If we take this out... and leave that. Let's isolate where this is happening. So this is quad 2. So is it in quad 2 or cubic 2 is what I'm curious. Okay, so it's still there. Let's see if it's just one or the other, if it's both of them. If we do this now. Harry Studios, this looks interesting. Are you going to make it open source? Been looking for a GPU accelerated path rendering system for a long time. So have I. Okay, we found where the issue is. That's good. And this is already open source. You can check it out. It's very bad code right now, but it is open source at least, and I'm trying to make it better. Here is a link to the GitHub. But basically, I'm using NanoVG, which is this thing, which is great, but it's super slow. SVGs were not meant to be rendered in real time, so unfortunately very slow. So I've built a whole caching system where basically it caches the SVGs up here and then uses that cache to actually end up drawing them and stuff. Still a work in progress, still many bugs, and it's hopefully getting better though. We've isolated this problem though. Looks like it's happening in here for some reason. So this all looks fine. We've got transform times that. It looks fine. I'm wondering what I did wrong here. And this is working, so this is fine. It's just this part that's got to be broken. So are we interpolating it wrong somehow? P1, P2. I have no idea what's going wrong, right? So if we remove this, transform P3 looks like it's correct, because if we do that, yeah, we get that, and it's actually going to the correct points. So that part's fine. I wonder, let's see all of them, because I think one of these is just messed up. What about P2? Is that okay? Let's see. Okay, that looks fine too. It looks weird, but I think that's fine. I'm checking to see, because I think one of these are not transformed properly, since it's going back down to the origin is what it looks like. That looks fine too. Okay, I have no idea what's going on there. I wonder if it's supplying this normal. So if we do line 2 here. Okay, that all looks fine too. But then if we do this, it's broken, or at least it was. Okay, yeah. And they're all going down to, oh, they're all going down to infinity. Okay, that's not good. I thought they were going down to the origin. So what is happening there? I think the normal is undefined is probably what's happening. Let's go back here. I'm curious. Let's go into here and see what happens. Okay, that's defined. That is defined. Let's go ahead, check and see if one of the other ones is broken. No, these all look fine. I'm not seeing undefined numbers. Weird. Okay. Yeah, and this looks right too. Huh. I wonder if we can catch that. Let's see if is there like float NaN? Not a number. Here we go. Is not a number. And let's give it normal.x or that broken. Okay, let's see if we hit this, because I think this is what's happening, since it looks like it's going to infinity. Nope, that's not happening. Okay, so the other thing that could potentially be happening is one of these is 0, but I don't think that should be a problem. So this will just do an epsilon compare to see if it's close to 0, because that could make it shoot off to infinity too if there's weird division happening. Nope, that's not happening either. Okay, I have no idea what's going on then. Let's try. Actually, not that. Let's try this with the interpolate point. Because it's going down and to the left. So something is less than 0 and like very broken. Okay, so we are getting this. What is this? Okay, yeah, this is definitely the problem. We're getting -2 times 10 to the 17th. So what's happening here? This is, okay, so this is bad. That's all bad data. What is... That looks fine. Okay, that looks fine. That also looks fine. But then when we get into here, it's all bad. No, okay, just P0. Oh, okay, I wonder what's wrong with P0. P0 is undefined. Let's see. Data has 2 elements. That position is defined. Or no, I guess this would be the second one because yeah, okay. So that would be here. Okay, and that position is defined also. Why is this -1 to the 18th power then, if that is 10.09? That's weird. What happens if I copy it? Do we still get that problem? I wonder. Okay, that's weird. These are fine. This is one of those things. So I was talking about how we have to bevel things if the miter join gets too big, and this is exactly why, because otherwise you get these artifacts. But that was really weird. I wonder why taking a const reference was breaking everything there. Oh, I wonder if it's because this was being resized in the middle of it. Yeah, okay. Okay, this is classic C++, right? Why the heck was that being undefined? Because we were taking a const reference to some point in a vector. And while we were doing that, this line 2 may have resized that vector, which then would invalidate that, and then all of a sudden we get undefined data in there. Okay, let's fix that because this is in 2 places. Let's fix that here as well. Not take a const reference and take a copy instead to ensure that doesn't happen. Yeah, classic, right? Voxerus, how's it going? Good to see you. And also good to see you, Raymarch. Okay, so anyways, though, that should fix the last of this. And now we can see we've got our paths. And if we go ahead and switch to the mesh view, we can see that we have nicely tessellated paths. So the triangles are getting formed properly. We do have problems like with this O, where if we have this straight up and join, the miter breaks because it's trying to get too high. And so we can do a temporary fix for this by basically just limiting it. I do want to figure out how to actually do this properly though. So maybe we'll try and do this properly. First, we'll see if the temporary fix does anything. If it does, then we'll fix it properly in a second. So this miter, the generate miter, I used to have this, which basically was supposedly, it's supposed to limit it and make sure that we don't get like very bad artifacts like that. And if we turn it on, you'll notice it does, but it's also not that great because you'll notice this is kind of crooked. We're not getting straight lines, and it's because it's limiting the miter too much. Whereas if we turn it off, just for reference, so we'll take that back out. And Miria4F, hello, it's going good. The app is going good as well. We're finally actually optimizing stuff, which is nice. So then you see if we don't restrict it like that, we actually get appropriate sized miters, and these are straight, which is nice. So the way that we fix this is we do it the proper way. Let's just get rid of that and that. We do it the proper way, and the proper way is by following the documentation here for what actual SVGs do, right? So once the join gets too steep, we cut it off, kind of like that. But how do we tessellate that is the real question. And I think the way we tessellate, we add an extra triangle, kind of like an inner triangle to get that tessellation. Sam, why would you don't set GLFW to the start maximize? You always click maximize. You know, Sam, that is a really good idea. I'm going to fix that right now. I don't know how long I've had it like this and just kind of dealt with it, but let's do that. First of all, though, why is this giant? Because I'm going to commit my changes so we don't lose what we've done so far. So let's do this real quickly. Git status, just make sure, yep, that's fine. Commit refactor 3D path rendering to 2D. Push. Okay. Thank you, Sam. I do have, if we go to window.cpu, the sad thing is, I think I have, do I have it in here? No, okay, I don't have it in here. I thought I had an API already. I probably do in one of my other projects that does that, where it basically sets it to maximized, but here, we can do this right up here. Window hint maximize true, let's do that. So this will be nice. Maximized. Maximized. Okay. Does this work? Let's see. True pros continue the curvature change over the edge when making their sharp corners. Yes, this is a nerd snipe attempt. Well, that's a different kind of bevel. So there are different ways you can bevel. We'll talk about that in a minute too. This is so much nicer, Sam. Thank you for that. One other change I made too was where basically, if we go to the main app, main.cpp, I also did this thing where basically it just automatically launches it. You'll notice it blinks a window. So there's a window that blinks into existence for a second there, and then it blinks into this one. And the reason is because I have that project selector, but I basically have it where if you opened a project previously, it just uses that. So if we actually look into here, in here, yeah, it does it somewhere where basically we just automatically select the project and then open up whatever you were last working on, which is nice. But yeah, this is a nice optimization too. Let's commit that. That one line of code change. Add dot. Make my life better. So let's keep going now. All right, cool. So in terms of beveling with cornered bevels, or rounded bevels is what I meant. You can actually change that. So we have this, when two lines stroke line join, it's possible for the miter to extend. The ratio of the miter, all that stuff. I think if we go into here, stroke line join. Yeah, so you can define like different kinds. So you get an arc, you can have a bevel, you could have a miter, you can have a miter clip, and you can have round. So round is round, miter is cut, arcs, I guess is this one. Yeah. Well, no, maybe I'm looking at this wrong. So arcs, bevel, miter, this is miter clip, and then this is round. No, that's not right. Okay. I don't know. I think their picture doesn't line up with this, but basically this is rounded and then this is miter. And you can have either one. The default one though is to just do this type of miter. But the good news is we can actually change out how this works and stuff by just changing the methods we use and everything. I don't know. So should be good. And Raymarch, I think that's a great example where you'd actually want the curve to continue when doing sharp. So I'm not quite sure, right? Because let's see, font editor, or let's do like, I'm just curious. And thank you for following Zoo2852891334. Good to see you. What is it called? Rich text editor online. I want to see what other people do when they outline a font. Like, what does the browser do? I'm curious. Let's do this. Okay, cool, yeah. So, hello world, right? I wonder if I can outline it here. Let's see, edit, no formats. No, can we not outline fonts? Maybe if I open up Microsoft Word. I never open up Microsoft Word, but who knows? Maybe this is, let's do that. Okay, hello world, right? Let's increase the size. Okay, can we outline it? We can. Okay, so they have this outline effect. Fill back, what is this? Fill blue, outlined. Okay, what do they do when they outline it? They get kind of curvy. Yeah, so it looks like they're curving around the edges there. I wonder if you can change that though, depending on which one you use. Let's see. Okay, so if we were to switch to that, still curved. That's interesting. Still curved, curved. All right, looks like they curve it. So that's Microsoft Word, but different things have different ways that they do it. So I want to check and see how a vector editor program does it. Inkscape is like severely broken for some reason. I might need to update it or something. Let's just get out of this. Inkscape, reopen it. I know that SVG doesn't do it that way and no vector editor supports it, but it looks so odd. And before they draw the font 8 times with offset. And that's true too, but I want to have the default settings the same as SVG since I'm aiming to make this SVG, like it is supposed to be an SVG editor and stuff, but I think most tools have the option where you can change that. Let's go ahead and change our font here to Arial bold. Okay. Maybe not this one. Let's do Consolis. There we go. Because this has some, well, okay, so no, this one is not quite. What font am I using inside my program here? And we'll use the same font. Okay, this is using Arial Bold. Okay, so clearly my thing is broken because it's doing that wrong. Oh no, here we go. And let's just double check. Okay, yeah, so we've got this kind of like curve that looks like the same font as what we've got here. Now, if we outline this, I'm curious what's going to happen. So if we do over here, stroke paint, and let's make that red. Okay, and then let's... I can't zoom in because Inkscape is just broken permanently, I guess. Looks like they do. So if you, I don't know how well you guys can see this because it's not letting me zoom in anymore, but it does look like they're just doing a miter here for that outline. And I think that's what I'm going to go with as well, but you can obviously too. So if we were to select this, we can change it. And I think most SVG programs have this ability where one of these things, yeah. So that's that. No, okay, maybe not that one. Well, I guess they're not giving us the option to switch the join, which is interesting. The join is usually what you would do to change that. And if we were to create just like a path here, right? So if we do that, let's increase that to 10. You can see we've got that shape. If we change the join to a curve, you can actually change that here, but for some reason, and then you can change it. But they don't give you that option for fonts, which is interesting. Let's see what you got here too. I'm gonna open this up on another screen though, just in case, because you never know, clicking on random links. Okay. So yeah, contour corners are always parallelograms. To continue the same curvature, yeah. So I would love to do this, except this is one of those cases where it's like easier said than done. It's very difficult to add in extra capabilities like this. If we can get to this point, I'll be pretty happy. I'd like to sketch out though, how are we going to get to that point? Because it's not as apparent as I would think. So let's go back to our drawing screen real quickly, see how we might actually end up doing this, and then we'll try and implement it real quick. So I'm going to go move over here. Okay, so the MDN docs basically specify like how you can determine when to split a miter. So our problem is, right, we have, whoops, say you have a curve that goes like this, and you have a really steep join there. What's going to happen is this is going to want to split out like this just to make sure that it maintains the same stroke width, right? So if we were to do this and we want this to be parallel to the lines, we would have to go down to there, go down to there. Maybe this isn't such a great example, but the steeper it gets, the wider this kind of join can get. And so instead of having it go like this, what we can do is we can cap it off, right? So basically we cap it off, and that cap is going to be perpendicular to the join. So what ends up happening is we have our bisecting vector, we can get a vector perpendicular to that, and we want to project it to our maximum outer edge, right, which would be something like this. And then I guess we would leave the inner corner alone. And then what I basically want to do is I want to build a triangle inside here. And then this triangle will connect to these ones normally. Right? So basically, I want to give the lines 2 extra normals here. And then I'll just add this triangle manually is what's going to end up happening. Let's see if we can actually get that done. Because I have no idea what how we're actually going to do this. So we'll see. Okay, if we go back to those docs here. Sorry, excuse me. So, when 2 line segments meet at a sharp angle and miter joins have been specified for stroke line join, it's possible for the miter to extend far beyond the thickness of the line. Yes, that's exactly our problem. We don't want this. We want it to cap off. This ratio, stroke miter limit, is used to define when that limit is exceeded, and then if so, it's converted from a miter to a bevel. The ratio of miter length, the distance between the outer tip and the inner corner of the miter to stroke width, is directly related to the angle between the segments in user space formula. So they give us this whole thing. For example, a miter limit of 1.414. This is basically just how you can define like what angles will end up converting to a miter. But what is stroke miter limit? I just want to see what the default value is. Let's check that out. Okay, so if we go down here, nope, it's not going to tell us. Let's see. Okay, I want to see what the default value is, though. I'm assuming you can figure that out. Maybe it's up here. 4 is the default value, according to CSS tricks. Let's see, SVG default value. Okay. I guess it says it's somewhere in here too. Specifications. Ah, okay, here we go. So we can get to here. Initial value is 4. Cool. So that's what I wanted to know. So we know that the default value for this is 4. And so now we know that we can get the stroke width, miter length. So now we can get the miter length, right? So if we just multiply this up, if we do the miter limit, which is 4 times the stroke width, if miter length is greater than that, then we want to convert to a bevel. So I think the best thing we can do right now is, first of all, let's go back into here. And we want to basically check and see. And let's do this. So right now, right, if we do this, this breaks a lot of our joins because it's not correctly limiting the stroke width at the appropriate places and stuff. Right, so if we do that, you'll notice the W is kind of slanted there, which isn't good. I can make that a little bit bigger. So it's a little bit slanted there. We want to fix that. Well, apparently if we use the stroke miter limit formula, we should be able to fix this just by multiplying the width times 4. So const expr. And then we basically want to check and see if that's greater than it. So float miter length equals this thing. That's the miter length. Bool should convert to bevel equals stroke miter limit times outstroke width, which is the miter length. And this is going to look a little bit weird because we're dereferencing stuff there. Is greater than, or no, the stroke width times Or I guess the miter length over the stroke width is greater than that, maybe? I guess I don't have to do any sort of fancy stuff here. Let me see that one more time. So if miter length over stroke width. So if this divided by what the stroke width should be, which we're getting past in there, is greater than stroke miter limit. Okay. So if we should see this only affect the lines that we want it to affect. Let's see if this works very quickly as a proof of concept. Okay, so these are straight. You'll notice this is much shorter. Okay, so that's actually working perfectly. So it's basically saying this one should convert, and you'll see too, this is messed up as well. So yeah, that's working good. It's detecting which ones, and I don't think, yeah, these look straight too. Cool, so it's correctly determining which ones. That's good. Temin, if you have a way of clipping polygons, you can clip the two polys with the plane that's perpendicular to the bisector. Or I guess you could call this a line instead of a plane in this case. Breaks a lot of our joints. Clipping polygons, you can clip the two polys with the plane that's perpendicular to the bisector. So I don't know if that's going to be easy. So basically, I'm trying to avoid like any sort of clipping algorithms because they're slower on the GPU. That's originally what I had this all doing and stuff. So we're basically just trying to tessellate, which is generating the geometry. I don't have any algorithm specifically to like clip the actual geometry according to a plane and then give us new geometry. So we'll just kind of like calculate the triangle by hand, and then we'll just use the new normals, and it should all work out, is what I think. Technically. So basically what we want to do is like here, if this is true, use a different normal. We'll have to figure out how to use a different normal that lines up to what the miter actually should be and everything. And Harry Studios, are you going to do dynamic tessellation according to the zoom level? I don't know. That's a good question. That's a good idea too. I should put that on the to-dos. For now, I'm not going to, because I'm just trying to get this kind of to a proof of concept as fast as possible. But that's a really good idea, because you clearly don't want to tessellate as much as you do if you're all the way out here as you do when you're in here. For now though, I'll just have it tessellated. It's not that many polygons. Like if we open up render doc, we can actually see exactly how many polygons there are. And I don't think it's that much. And I actually, no, okay. I just closed it down. So if we go ahead, I think I can do like launch. Yeah, load last settings. There we go. So that we can see exactly how big the draw call is and stuff. So then if we do F12, we've got that right here. And this is all batched together too. So if we go into here, this is right in here. So there's a few draw calls. And this is just because of, I think this is because of texture switches or something is what this should be. Now I'm curious. So that draws that. Oh yeah, I should switch this because right now it's basically swapping textures for each letter and then redoing that. But yeah, so like this is 72 triangles. Ooh, this is almost 1,024. Yeah, so it is using quite a bit of triangles, but it's not that bad. I don't know. That would probably be a good idea though. So I will have to keep in kind of like LOD for this stuff as we go forwards. But yeah, if you're rendering a large body of text, I guess this could be a lot of vertices. Although, are you going to do instance rendering on individual characters? Instance rendering would also be a good idea, but unfortunately I can't do that because of the way this is supposed to be rendered. So the whole reason that I have these is because, and that's not right. We're going to have to fix that. So this is the connection that I don't want to happen. But basically, we can't really instance render them because the different, right now, these O's are in the same state, but you can have these kind of offset where it's creating this one first, and then these are all lagged behind. And so you won't really be able to reuse them since they'll be in different states at different times. But we'll see. I don't know. I'll have to think about all this stuff in the future. For now, this is already way faster than what I had before. So I'm pretty happy with this. I'm going to go take a break very quickly. I'll be back in like 5 to 10 minutes, and then we'll continue with hopefully this bevel is the next part. So we're going to finish a bevel, and then I think that's going to be the end of the stream once we get that up and running. So I'll see you guys in 10 to 15 minutes. All right, guys, I am back, and I think I've got an idea of how to do this. Thank you, Temin, for your suggestion on clipping. So I think the plan here is basically, right, we get this green line is the miter. If it's too long and we want to split it, we want to shrink it down to this point, right? And Temin, you mentioned clipping. I think that's exactly the idea we want to take. And how do we clip this? Well, what we do is we say, okay, we only want the miter to extend to, say, this point right here. And then we can project this onto this line right here. And this line, in this case, is just the direction of this guy. So we can project it to the left that way for this point. And then we can also project it for this incoming angle, which would be here. And then that will give us this point. And then this last point will just be wherever our center point is, right? And so that will give us the normals. And it will also give us the length of these normals. Yeah, and I think that'll work out. And then we can just add this triangle. What we're going to do for now is we're just going to try and get that triangle up. And then if we get the triangle, then we know we're in business. So let's go and try that out first. All right, so when we're generating a miter, if we need to convert it to a bevel, we basically want to shrink it, right? And how much do we shrink it by? That is the question. Does it give us an answer? It just says it's converted to a bevel. Well, how does a bevel work? Let's see. How does SVG bevel work? Actually, I might be able to find better information here. This thing has some good stuff. Okay, yeah, so this has the rounded bevels, and then I thought they had regular bevels too. Okay, this. Or maybe that's what this is. Take the outer corner of the two lines and connect them to form a bevel. So that's basically just... See, but how long is that interior? That's what I'm concerned with. Okay, let's see if we can get that here. How long does an SVG bevel to be? No, see, everything with SVG brings up a bunch of like HTML stuff and everything, which is not very helpful in 99% of the cases. OpenGL graphics. Let's see if this gives us anything. Nope, that's not what I want. And then I get this thing. Okay, well, I guess we're just going to wing it then because I'm not seeing anything. So I'm going to assume that what we want to do is just set this to the stroke width. This. Oh, wait. Actually, no, never mind. Look, it shows us right here. How long does that outer edge need to be? It's where these two lines join, where they meet. Oh, okay. So we basically want to connect it wherever this hits that one, where the intersection of those two lines are. Okay, so how do we find the intersection of the two lines? That should be easy, but my brain is not working today. Let's see. Let's just Google it because that's going to be easier. Okay, so let's see, intersection of two lines. Well, let's do of two vectors. That's not what I want. Maybe this one? See, I don't like when everyone gives their answers in these. Like, I get that math is useful and everything, but I don't need super complex mathematical equations. I just need some code. Stack Overflow. Yeah. Okay, I don't know. I think I'm just going to wing this too. So let's go back to the drawing screen real quick and try and prove this out for real. So let's go over to here. Okay, so basically what we want to do is we want to actually cut the bevel right here. This is just going to be wherever these two lines meet. And so where do those two lines meet? And then I guess we just like create a triangle to that interior corner. And we can figure out where the two lines, actually, I am an idiot. The two lines meet exactly where this vertex is. Oh, that's a lot easier than I thought. Okay, so never mind. This is much easier than what I initially thought. So basically we just need to project from that vertex onto each outer edge. Okay, so we need to project. I'm trying to think of how that's going to work. So basically, I think what we want to do is something similar to this, right? So we did the dot product of the bisection and the second line. And what I want to do here, let's just try this. So I think what I want to do is say vec2, or I guess like float first bevel width equals, and then figure out how to get from one point to the next. So basically what I want to do is the dot product between the bisection, which in this case, this is technically the perpendicular and that's not. So let's actually fix this. So this is perpendicular. This is not. That should be that. That should be that. And I think that's right. Okay. I think what I want to do is take the dot product between the perpendicular of the bisection and what our incoming direction is. So that would be direction A. And then I think I want to say stroke width over that. And that should give us how long we go from there to that one. Vangarioth LP. Please code, no math, only code. Yes, I agree. Exactly how I feel. Okay, so then the second bevel width, I think we can get by saying stroke width over. We want to take the perpendicular with direction B. First of all, let me just make sure when I changed that naming, I didn't mess stuff up. So let's just make sure this is okay. We should get the same thing we were getting before with any luck. Okay, cool. So you can see we're getting messed up here, but that's just because of these edge cases we're trying to fix. And what I'm going to want to see is we're going to try and form like a bevel right there. I guess technically where these meet. So like right here is where we want to see it. And thank you, Vangarioth LP, for following. Good to see you. Okay, so I believe this is what we want to do. So we have the first bevel width, we have the second, and basically to get the triangle points, we get our first point is going to be our bisection perp. Basically our current point plus the bisection perp times the first bevel width. Hopefully. And then our second point, I believe, is going to be current point plus bisection perp. And we're actually going to be doing minus in this case. And then for our third point, we want where the inner miter is going to be, which I think is going to be P3 equals, I guess we'll call the center point, equals the current point plus the bisection times the outstroke width. I don't know if we want to do that though. We'll see. We'll see what happens. I have no idea what's going to happen here. And let's also do, we're going to say push color. We're going to make this RG. So green. And then we're going to say line 2. Or no, we're actually going to just say filled try. First point, second point, center point. And then pop color. Okay. So let's see what that does. And also, Vengariath, usually I'm watching your YouTube videos because I never make it to streams. All good. Hopefully I'll be making YouTube videos at some point again. Raymarch, is perp perpendicular? Yes. I probably should have made that a little bit more clear. But yeah, perpendicular to whatever the other one is. Yep. Let's see what happens here. Do we get a green triangle that is the miter join? Okay, actually, this doesn't look very good, but I think this kind of is good. Yeah, okay, so I think I just need to cut these in half. I am very surprised that that worked at all. I was totally not expecting this to work, but it looks like we might have actually gotten what I was looking for. So if we just half that, because we actually want to go halfway out instead of the full way out. Do this again. Yeah, oh, okay. That's I think that's exactly the bevel we want. And then if we go from here to here, is that going to give us the same stroke width? See, that's where I just need to figure out the length of this. I don't think that length is correct. Like if we go from here to here, that's not going to be uniform. And definitely for this one, this is definitely not going to be correct. So how do we get this? I guess we just want to make sure that this is shrunk so that this equals the stroke width. No. We want to make sure this line from here to here equals the stroke width and from here to here equals the stroke width is basically what we're trying to do. Those are our constraints. How do we make it so that this triangle fulfills those constraints? We know we need this to be perpendicular to the tangent, to the bisector, perpendicular to the bisector, which it is, so that's good. But then we need to figure out what the length of this is and where to place that center point. And that center point is going to be along our tangent. Okay, so let's go back to the drawing screen very quickly. We're getting close. Almost have it. And that topic is wrong, by the way. I'm not learning Vulkan right now. We're doing something completely different. Okay, so let's go back here once more. We've got something that looks like this. Okay. And so basically we have our perpendicular, or we have our bisector. Our bisector looks like this. Right? Just goes right through the middle. And what we want to do is we want to take this guy out so that it's perpendicular to this blue one, right? So we want this to be perpendicular. And we need to find the length of this such that this stroke width is going to be half this distance. And we need to find the length on this side such that this stroke width is going to be half this distance. So in order to do that, I'm wondering... Geometry was never my strong suit. I'm trying to think though. So basically, how do we ensure that this point is such that this equals half of the stroke width? So this should be equal to, we don't know what this is. This is X, right? Or no, we do know what this is. This is half the stroke width, right? So we'll call this W. These are both W. They're the same. We don't know what this is. This is X. So if we want to find what the length of X is, we know the direction. We know the unit direction of it. We just need to find it so that when it intersects with this point, it equals W. Oh, and that's just projecting it onto this, right? Yeah, which is what I'm doing. I think that's what I'm doing. So basically what we have, right, is we have something coming in here. We know where this line should be, right? This is the start, this is the end point. Oh, I know what I'm doing wrong now. Okay, so basically this is a unit vector. We have the direction. We want to project this unit vector onto not a unit vector in this direction. We want to project it onto that full length vector. I think that's the problem. Let's try that real quick. If it's not the problem, then I'm just spouting nonsense. We'll see what happens though. Let's go back to here. So basically, I think what I want to do. Okay, so this direction A, it's normalized. We don't want it normalized. I think I literally just want that instead of that. And yeah, I think that's it. Let's see what happens. So that should change one of the halves of that triangle. Let's see what that does. Okay, I think that's right. Wait, no, I'm looking at the wrong one actually. I think that changed this one, which this is definitely wrong. So it looks like this is going all the way out to here. Let's just see this real quickly. How to project a unit vector onto a line segment. Let's do that. Let's see if this is helpful. Okay, yeah, so this is, we first consider orthogonal projection onto a line. To orthogonally project a vector v onto line L, mark the point. So we basically do that. Yeah, so if we have this unit vector and we want to project it onto there. Oh, am I thinking about this wrong? No, I think I'm thinking about this right. Possibly. Wait a second. I might be thinking about this backwards. Wait a second. Let's go back here to the drawing stream. Let's go over here. Okay, I think I'm thinking about this backwards. So we're not projecting this guy, right? I think we are just projecting this vector onto here. And what is this vector? This vector is this. See, this is where I'm... It's just this point. Let's look up how we can actually project vectors, and we'll do the full projection, because technically dot product is not a full projection. That's just kind of a shortcut for when you're projecting unit vectors onto each other, which is not what I want to do in this case. So let's look this up. For some reason, it's always hard to find how to project things. They don't have any simple equation. Like, I just want to look up Wikipedia. Here we go. Projection, linear algebra, Wikipedia. Thank you. So orthogonal projection. Yeah, we do all that. Properties and classification. I don't care about that. I just want to see how we can actually use it. Okay. I'm just looking for the main equation in all of this stuff. I don't get why they don't have a big section that's just like, this is the equation. Okay, formulas. Okay, so if u is a unit vector on the line, the projection is given by the outer product. No, this is not what I want. Okay, let's do this. Programming. Project vector onto another vector. They're just going to use NumPy. Okay. About this one. So if I have a vector and I want to project onto that, shouldn't that give me a vector of 0, 9, 9? Oh, okay, so it is just the dot product. The vector dot the normal times the normal. So yeah, so if we project this vector onto here, so if I do, instead of this, that, why is he multiplying by the normal afterwards though? Oh, they're projecting this vector onto the normal. Okay. And that's the projection. Okay, I see now. So what we want to do in this case, this is why I don't like math, even though I did major in it. And I can see the viewers all dropped off. Nobody else likes math either. Okay. So in this case, we want to project this onto this unit vector? No, we want to do, so this is our vector from here to here is our vector. And we want to project this direction onto that. That's what we want to do. So in that case, we would project the bisection not the bisection perpendicular. I'll leave that the same for now. Or maybe that was that too. We want to project the bisection onto that vector, which is just current point minus previous point. Yeah, so that's what I was doing. Okay. And then he's multiplying by the unit normal afterwards. Which in this case would just be that, I guess. Okay, let's see what happens. So if we do this, does that give us... Oh, we want to get... Whoops, that was not what I wanted to do. Okay, let's go back. So let's just do that. We'll say that. Get rid of that. What happens here? Does that give me what I want? I have no idea. It does not look like it does. That looks even worse now. So it looks like we're going all the way out to here, which is definitely not what I wanted. Maybe I am projecting onto the wrong curve here. Is this supposed to be perpendicular? No, we get the same thing. Oh, well, I guess in that case, I would have also multiplied by that. Here, let's try this one more time. This is usually what it always comes to, is just trying a bunch of random stuff until something works, which it should eventually. Oh, I guess, wait, no, yeah, that's fine. So we have first point. Yeah, and that's... Yeah, and I think that's exactly how I would want to do it in this case. Current minus previous, yep. What happens if I don't do that? And I do this. It looks like that took it even further. Oh, wait, I think that was working. I was looking at the wrong one. Wait a second. Okay, let's go back. Okay, if this was working, then I've been looking at the wrong thing this whole time. Wait a second. Okay. No, yeah, that goes out even further. Okay, so that's not what I wanted, but maybe if we do... that one. I don't know. One of these has to work. No, I don't think that's working either. Okay, so it doesn't matter. I was looking at the wrong one the whole time, and it still wasn't working. So let's change this, though. I want to fix the other one that was broken before, which I think if we just do that... I think that's what we want to get that working right, and then we'll see. How's it going? Good to see you. Itakashira. I'm probably saying your name horribly wrong, and I'm sorry about that. It's going good over here, though. Hopefully you're doing all right, too. We are trying to do math and horribly failing. Okay, so that looks fine, I think. Maybe we'll want to do that, though. Nope, that doesn't look right either. Oh, wait a second. Actually, one of those points did look right. Did I accidentally just calculate it? No, because we should be going... There should be a point like right there is what we should be getting. Or actually, no, I don't know. This might actually be right. Wait a second. Okay, maybe I did accidentally just figure it out somehow. But this is what we had before. So in that case, I'm not sure what's going on. And thank you for following at Porto. Thank you. Let's see. So if we do this onto A... No, that should actually be the same thing, I think. No, yeah, that's right. Okay. This should be first bevel width. Okay, let's see what happens now. I don't know if it's intentional, but I can't see anything. Oh, you cannot. Thank you, Takashira. I'm sorry if I'm saying your name wrong, too. I never switch back. Okay. That would have been helpful. Thank you for letting me know, except for messages in chat. This is what you should have been saying. So hopefully you guys can all see what's happening now. That's going to be bad for anybody who's watching this later. Okay, maybe we want to do plus in both these cases too. I think we just did it. I unintentionally figured that out somehow. Yeah, I think that's right. So these are now cut off, and it looks like it's clipping the polygon at the right point. Okay, that's good. And then I just need to somehow get that point in the right position too. So basically now what we need to do is make sure that the width from here to here and from here to here is the same. Which should hopefully, I don't know, because otherwise we get artifacts like this. And I think we can do that just by doing something like, I think we might do an interior bevel there too. Let me see what they say here. Yeah, I think we just do another thing here. So we do like kind of 4 triangles here. Nope, these link in a triangular shape though. Let's see. Okay, so my intuition says if I just do this times the stroke width times 0.5. That's basically all I need. That's what my intuition says. I have no idea if that's true or not. We'll try this and see what happens, and then we can go from there. Okay, that does not look right either. Let's see, what did I do wrong there? So current point plus the bisection, which should be a unit direction, right? Unit normal, yeah. What happens if we just do times the stroke width? I'm curious now. I might just have to do minus there is what. No, that still looks weird. Oh, maybe I'm supposed to, no, yeah, this is right, okay. What happens if I normalize this? It should already be normalized, but I have no idea if it actually is. Let's just try that. And then if that doesn't work, I'm gonna do minus and we'll see if that works. No, we still don't get, yeah, so it is normalized already. What if we subtract that? Let's see what happens here. By the way, I can just call you Eta. Okay. That's a lot easier. Thank you. Okay, so minus just flips the direction, which is what I would have expected, but I did want it in the first direction anyways. So that should be plus. Not sure why the stroke width is so small though. I'm not sure if it's the stroke width is small or if this is just wrong. Okay, let me see what happens if we just exaggerate this and do times 4. That should push it out further, but I just want to make sure. Okay, so it does push it out further, which is what I would expect, right? So it pushes it out to there. And what I want to be happening is it should just be like, so the width of this is what that should be, but it didn't look like it was doing that. Let's see, where's this? So this is getting called from here. Yeah, so that should be fine. Okay, well, we'll just go with this. Let's check that one more time. Yeah, I think what I need to do, so basically what I want to happen is the length from here to wherever that point ends up. So I need to do one more projection actually. So then, okay. What I need to do is project this onto this guy. So let's try that. One last projection and see if that works. So then float center bevel width equals, we'll do that over the perpendicular to, I think, the first point. Well, I guess technically we're projecting the first point onto the perpendicular. Okay, let's try that. And then this should be that plus or times the center bevel width. Okay, let's see if this gets us what we want. I have no idea at this point. What am I going to use this one for? Are you just learning? This is going to be eventually used to make animations and stuff. Hopefully. That is the plan. We'll see if it actually works out or not. But yeah, I'm trying to see. Okay, is that right? So dot product shouldn't matter which order you do these in, but I want to keep it consistent. Oh, I probably just want to do the direction of the first point. So we'll do normalize that. Okay. Let's try that out. And cool, thank you. Yeah, so we'll see how it goes, but basically this is gonna be used for creating animations and stuff, is the plan. So like, as you can kind of see, like, as I go through the timeline over here and actually turn it on, it's basically like writing in these letters, but we're trying to get it so that this is working properly. So these miters are too big, and so I'm basically trying to make sure that it cuts it off right there, and then we get a point in the middle there. But it doesn't look like it's working out the way I want it to. Yeah, that's so weird. I don't get why it's so small. There's no way that's the proper width. Maybe it's because I'm doing 0.5 and I actually want to do the full width now. Let's try that. That still doesn't look right though. Is it? I don't know. I wish I could zoom in more. We can pop this out. Whoops, wrong one. Let's make this bigger. Is this the same width as this? Or I guess this is what I should be checking. I don't think so. I feel like this needs to be up higher in order to get the same width. Oh, wait a second. No, I think what I want to do is project this direction onto this vector. And then that should give us where that center point should be. I have no idea if this is at all right, but we're just going to try that out. So project this direction onto this vector. So that's that onto that. Let's see what happens there. Okay. It looks like it's projecting it the opposite direction, but that definitely looks closer to what I would imagine it would be. Yeah, but then we're getting the same problem we have down there. Oh, and let's make this plus again. See what happens there. Okay, yeah. See, this is what I would expect it to be. Is like, that looks correct. Let's just pop that out. Make that bigger. Yeah, that looks correct. So this will end up giving us, if that connects down to that point, a consistent stroke width. But then we get the problem up here where you get stuff like that. And they don't talk about what to do about the... Yeah, the interior joint, if that one starts going too far. I guess maybe I bevel that as well. I have no idea. Well, let's try and fix this one at least. So I think this is correct. We basically just want to chop off that, and then we should connect to here. So now we have the normals. Let's see if we can use them. Okay. So in this case, I think what I want to do is we're supposed to output a normal and a stroke width. And I think what I want to do is say star out normal equals, we want to do normalize from the first point minus the center point. So that's the normal, and then the width is going to be out stroke width is going to be the length from first point minus center point. Yeah, okay. Let's see what happens there. I think that should fix the second half of this, but we'll see. Okay, that definitely did not fix it. I think I have it backwards. So if we do second point, let's try that maybe. See what happens. Nope, that's not right either. Basically what I want to happen is it should just connect into these, but I'm not quite sure how to make that. What if we reverse it from there to first point? The length shouldn't matter, but I want them to be the same, so let's do that. See what happens here. Nope, that's not right either. Try one more thing, and then I'm just gonna build it manually if this doesn't work either. Do that. Don't think this is gonna work, so we might have to just build this manually. Yeah, okay. So instead of doing this, I think what we want to do is basically say we want another triangle from the first point to the center point to the previous point. But this is where it gets kind of hard because that's basically going to go in the wrong direction. Let's see what happens here first of all. Okay, so we don't see anything there, but if we look into here, let's make it a blue so that we can actually see what's going on here too. And we'll do 0, 0, RG, this is B. Okay. Do that, let's see what happens. Okay, yeah, so that's kind of what I was expecting. So the only thing we want to change is we want this point to be from here to here. But other than that, I think this is correct. So we just want that to go up to there. Yeah, I think that looks about right. So let's do this. Generate miter. Let's do, this will return a bool. If we can't generate a miter, we'll return false. I guess we could just return should convert. We'll just return that. Should convert to bevel. Let's rename this. Okay. So we will return whether we can or cannot draw the miter. If we cannot draw the miter, then we want to convert it to a bevel. And to convert it to a bevel, we're going to need a little bit more information. And so for that, I'm going to do static void generate bevel. We're going to do this. That and that, and then I think we're gonna need a few more things. So we're gonna do this vec2, and then I think that's it. We're not gonna return anything from this one. Okay, so we're gonna do that. Basically redo all of this stuff too. So maybe I'll abstract this out into its own function at some point. For now, this is fine though. Okay, let's go here. Have this return bool. Okay. And then I basically want to say, okay, so bool should it draw line equals true. Let's do that. Well, okay, wait a second. So we've got this. So we basically get two normals and then two thicknesses, and that determines how we should draw a portion of the line segment. This is trickier than I thought it was going to be. Okay, scratch all that. We're going to do the original method that I was trying to do because I think that's actually going to be easier. Keep going back. And hopefully this works out. Okay. So essentially what I want to do is I want to return a normal that they can use to actually draw the line segment, but I'm not sure how to do that. Let's do out normal equals, let's see if we can just get the correct normal first of all. So let's try that. Center point minus first point. Let's try that. And then we're gonna say out stroke width equals stroke width. Okay, so let's see what happens here. And then this should be drawn in blue. Well, actually that's not gonna be drawn in blue. Let's get rid of that blue triangle real quickly. So let's get rid of this. See what happens here. Okay, so it looks like we're going from here down to here. That's correct, I think. Real quickly, I gotta change how far I can zoom in because I don't like this. Let's go to editor, settings, zoom. We have that. Yes, okay, and I want to decrease this. Or no, this is fine. Let's see. Let's look for zoom. Timeline, we've got the camera. Ah, this is what we want. Here we go. So let's clamp this even closer so that we can zoom in more. That should give us 10 times more zoom, I think. That's better. Okay, so now we can actually see what's going on here. Cool. So it looks like this triangle is going down to here. Okay, yeah, so that's almost correct, I think. Or actually, wait, that does look mostly correct. It's just that we have to fix this one, which is going down to here for some reason. And instead, I want that to actually... Well, no, I think I want this one to go up here. I think that's what we want. Yeah, and then we want this one to also go up here. I think that's what we want. But it is kind of beveling. And that shadow is not actually a shadow. It's just the SVG being interpolated there. Okay, so I think we're almost there. So I think we have the wrong normal still. Let's go down here. Out of here. Let's try that minus the second point, see what we get. Okay, I think that just flip-flopped it. Basically, they're just flipping from there to there. Yeah, so this is the problem. It's like I need to get this function to work correctly for both edges. Let's do this. Okay. This will take in a bool. Okay, bool here. Okay. And then down here, we're going to say this. Otherwise, we're going to go to the second point. Or maybe this one should be the first point. That one should be the second point. And that's going to be true. This one is going to be false. Okay, let's see what happens here. With any luck, it should just work. Hopefully. If we run that. Okay, so not quite working. Let's see what happens if we flip them. So if I make this false and this true. No, they're still going to that bottom point. Okay, let's try one last thing. Just go back to there and then up here. We're going to do negative. So let's do that. Oh, and I think that's what I should have been doing all along anyways, is we should have been going this direction. Yeah. Okay, let's try that. Nope, that's still not working. Well, is it working? Let's see. Oh, you know what? I'm not thinking about this right. This should be the normal coming out of here. I am not thinking about this right at all. So instead of doing this, what I should be doing is that equals the bisection, just the bisection. I think that's what it should be. Maybe the perpendicular bisection. I'm not sure. Yeah, I think it should be perpendicular. Is that what it should be? Yeah, perpendicular. Let's switch that up very quickly. Which it already is, I think. So let's actually not do anything to this and see what happens. I might have to do negative. So if I flip this and do that, is that what I want? Hopefully. Nope, it's still not working. Okay. Okay, I'm going to have to debug this a little bit more on my off time. I think I have to do some bigger restructuring to get this working. But for the most part, we've got like... we have it working for the most part. I just have to get these bevels working so that these inconsistencies get ironed out. And we already have the bevel triangle, so we're mostly there. I just need to actually combine these triangles into the appropriate shape, and we should be good. The reason it's so difficult, too, is because in order to combine them, I need to know where this point is and this point is. And in order to know where those are, I basically need to calculate the same thing here. So it's kind of like a recursive problem where you need the previous one in order to get to the next one, which is a bit annoying until you get to the very end one. But we're almost there. Once we are there, we can have this animation working and it should look correct and not as bad as it does right now. So anyways, I hope you guys enjoyed this. Sorry, it got a little bit off tangent there at the end with trying to get this stuff to work. It just requires a lot more focus than I can devote to it while streaming live. So anyways, I'll see you guys next time. Hopefully we'll have a lot more progress on this by the time I see you guys again. All right, have a good day.